Thank you everyone for joining this Trinity webinar where we are presenting the SME services Trinity network in Finland can offer for the manufacturing SMEs. And this webinar is divided into two different parts. First one will be focusing on the services for the SMEs provided by Tampere University and CENTRIA University of Applied Sciences, who are both part of the Trinity Core Consortium. Then after about an hour, we will change to Finnish and we will go through the Trinity open call, which has been open for a month now and is open until the beginning of June. So thank you very much, and I'll give the floor now to Professor Lanz, who is the coordinator of Trinity project. Go ahead, Minna.
Welcome from my side, and hopefully you can see my presentation now. So in brief, the Trinity project, it's about networking, building of new clusters for the companies and other stakeholders to find solutions to the problems and challenges in the field of robotics, ICT and cybersecurity. In Trinity, we have three assumptions which we set before the project was started, and we still believe on those three assumptions. And what we claim is that we can increase the product quality and production capacity by applying advanced robotics into the field of manufacturing, including the high mix, low volume production. Then we also claim that we can shorten the overall production time with applying ICT solutions and perhaps even artificial intelligence solutions for the manufacturing. This means, in effect, that we are decreasing the non-value added time in the production. And the third claim is that we believe that the companies and other stakeholders, including the RTDs, universities, can benefit from the industrial ecosystems, such as these digital innovation hubs can form. We will have limited resources in future, and in order to answer the changing customer needs, we believe that the collaboration is necessary. And in such, the digital innovation hubs can help to find the collaborative partners. In Trinity, we had main objective, of course, is to create the network of digital innovation hubs. So we want to have established network of competencies around the Europe. And on that, we want to create the sustainable business model so that our network will be there for the next 5 years, for example. So we are looking to the horizon 2 with keeping up the network. And the third objective is to create the critical mass of use case demonstrations, which are assembled of different technical modules that can be reconfigured to fit the different purposes the companies may have. And in relation to today's topics, we will go through the services relating to this utilization of these different modules, which we hope that are, of course, suitable for the upcoming open call number 2. This was a very brief introduction to the Trinity project and the topics of today. And in the Finnish part of this session, we will go through this in details. Thank you.
Yes, thank you very much, Minna, for the introduction. So let's move forward on the program. So the next two presentations will be about the services and examples of the services what we can offer to the SMEs during the projects and why not also after Trinity. So give me a second. So the Trinity services by Tampere University available for the SMEs. In general, Trinity services don't cover only the technical services given by the partners where we have presented these technical modules and use cases, what Minna mentioned also in her presentations, but also we have partners who can help you with consulting and business support. Mentoring and training services are mostly focused on the participants of our demonstration program, out of which you will get an introduction in the last presentation of this session by Hugo Marques. Then networking and matchmaking services to find the partners for the coming projects and also the general needs of the companies for networking and improving their manufacturing capabilities. Visibility and outreach we can provide for the partners of the Trinity network. And then of course funding in the form of these 2 open calls that we are organizing during the Trinity project. The partner network covers SMEs who will give us insights on the needs of the manufacturing companies in Europe. We have a research institute, we have university partners, and then we have also management and funding related partners who will support you during the Trinity project. So basically, if you need any help from the network, you can contact the closest partner within our network. The services by Tampere University offered during the Trinity, they are of course focusing on the 3 Trinity topics: robotics, Internet of Things and cybersecurity. And in case of TAU, we are mostly focusing on the robotics. We can provide technical workshops and facilitation sessions which can be related to your manufacturing, but it can also be related to, for example, writing an application to the open call. We have equipment available for hands-on training sessions on collaborative robotics, human-robot safety and other topics where we have expertise. We can help you with the application writing by giving tips and hints and discuss your applications. We will not write the applications for you, but we can certainly help. And then we have the technical modules that have been provided during the Trinity project. And the 3 modules by Tampere University are the projection-based interaction interface for human-robot collaboration, depth sensor safety models for the human-robot collaboration, and then wearable augmented reality-based interaction interface. And one possibility how to implement these modules again will be presented in the last presentation of this session. And related to these modules by Tampere University, we can provide you a bit more technical support and guidance how to use these modules and utilize these modules. All the code is open source, so you are free to use that and, for example, implement it in your own demonstration. They will later open a Trinity training platform where all the Trinity modules will be accompanied by different training material on what are the possibilities of these modules, how to implement them, how to use them. So they all come with the built-in training modules as well. But this work is still going on, so not all the material is available yet, but it will be coming bit by bit to our YouTube channel, and then it will also be listed in this training platform. And the help we can give you with this is a kind of guidance and technical support, but if it requires more hours or more research for work, then this needs to be negotiated case by case. And this applies to all Trinity partners. They have resources for help you, but those need to be negotiated with the partners. Training and facilitation services can include, for example, half-a-day sessions with Tampere University experts on the topics listed here. And this can be related to your application writing process, technical training or hands-on training. These are just a couple of examples what we have to offer, and feel free to contact us and request if you have any other needs. And that concludes the part of Tampere University services for Trinity. And now we move to Sakari Pieskä from CENTRIA, who will be presenting what kind of services CENTRIA has available during Trinity. Go ahead, Sakari.
Thank you, Jyrki. So Jyrki mentioned the Trinity services in general, and you should look from the Trinity Robotics EU webpage. There will be information about, for example, coming networking and matchmaking events, which will be during the March, April, May, before this open call 2 ends, and of course later also. But let's go to have a look from the overview of CENTRIA services for SMEs. So we have worked with different work packages in Trinity project. For example, work package 6 is for business planning, work package 7 for training platform, and we have looked at different partners, what kind of services they can bring to the SMEs. And here are the list of CENTRIA's services and how they affect to customers' value chain, market sectors what are covered, and technological specifications and unique expertise. So in the value chain, as Minna told, that the Trinity project is towards more agile and more versatile processes and improved product quality, how they will be doing. This will be done via technological development. And the market sectors in Trinity, the most important is manufacturing. There are a lot of companies also in agriculture which can use the same kind of technology. 5G network is coming, and communication technology in that way is also a possibility. So we can, for example, test. We have been testing in our laboratory this pop-up 5G measurement, 5G network, how they can affect production. And there is also cybersecurity is very important part of robotics because usually the robots are quite vulnerable in industry, but there are possibilities how you can solve these cybersecurity issues also. And then there is simulation, and CENTRIA has a strong expertise with close collaboration of SMEs. And here are the main topics which CENTRIA offers for Trinity-related services. And we have concentrated on Industry 4.0 technology, and we are offering analysis, demos, workshops, training, and different kind of experiments with them. So we can do consultations and also consultations for funding and application writing, as Jyrki mentioned. And for robot and cobot applications, we usually start with simulations, then we go to proof of concept or demos, and there is also a possibility to use experiments either in our laboratory or in SMEs production facilities, and we can use we can offer also training, for example, for robot programming or for robot simulation. Same thing is with the safety systems. We usually start from simulations, then we can go to demos and experiments, and often we also create a digital twins or robot cells or production lines if we are going to have a longer collaboration. Reverse engineering, which means 3D modeling, 3D scanning, and it can also lead to 3D printing is often used. And for example, in the picture above, there is a 3D scanning which can be used in real time for scanning the 3D model for the tank, and then a robot can make the washing lines, and Tero, Kaarlela will later tell more about this. And we have used different augmented and virtual reality applications, so there are some examples of them. One way to collaborate with the SMEs is workshops. We have had a lot of different workshops on different topics. For example, here is one example of augmented reality workshop where there was tens of SME personnel which were testing different kind of solutions with a company who provides these solutions and applications, also the equipment, and they could test and how they could fit to their needs. Then in the right hand above there is one example how ABB Robot Studio can be taught with VR glasses, and here we had an industrial management group with students from 10 different countries which were also testing this possibility. And in the right below that there is an example which Tero also will tell a little bit more. We made in January a demonstration or training session with a student group from Narvik University of UIT University there, and the idea was so that they made programs for our KUKA robot cell, and then they could also test it directly via network, and it worked very well, and Tero will show examples of this. So now, after last summer, we have fine equipment in our robot 3D lab at Ylivieska, so we can use it in our research and development projects, but also it can be tested by our SMEs. They can test something, and one specialty is the hybrid safety systems, which also Tero will tell more. It is a combination of safety approved safety sensors and also assistive safety sensors which can be added there. So our use cases and modules are collaborative robotics in large-scale assembly, material handling and processing, and there is 3 modules related to that, and also the other integrating digital content and to the digital twin and AR VR of the robotized product includes also 2 modules. One is common with the other one. And Tero Kaarlela will also go for deeply for these modules. And you can find also the modules and these use case demos in the Trinity Robotics catalog from our webpage. So if you need more information or help from CENTRIA services, please contact our Trinity trio, Tomi, Tero and me. Thank you.
And we start by Tero Kaarlela from CENTRIA, who will be providing the technical developments reached at CENTRIA. Go ahead.
Okay, my name is Tero Kaarlela, and I will be presenting CENTRIA use cases and modules for Trinity. First of all, let's look at our topics for this presentation. First, we will be looking at basics of Trinity module use case structure. And next, we will see presentation of CENTRIA modules for Trinity, and after that, we will move on to use cases for Trinity. And lastly is my personal favorite, digital twins for robot cell remote control and remote collaboration between organizations. Trinity modules and use case basics are that each Trinity partner has created a set of modules for Trinity, and by combining these modules, different kind of use case scenarios can be compiled. CENTRIA has prepared 4 modules and 2 use cases for Trinity. Our use case ideas are based on needs and ideas from local companies near us. So first we have the modules, and when these modules are put together, it will combine as a use case demonstration. First of our modules is safe human detection in collaborative work cell. Idea of this module is to provide flexible safety solution in order to provide agile working space for robots and humans working together. And on the picture right is our hybrid safety system in our robotics laboratory currently. And this module consists of multiple safety approved devices such as laser scanners, microwave radars, and safety light curtains. Additionally, this system also has safety devices for improved safety such as indoor positioning and 360 camera systems. And let's move on and see video of our hybrid safety system. First, we will look at safety approved devices in this system. First is the light curtain in front of industrial robot cell. Second is laser scanner on the right side of the robot cell. And then we have laser scanner and microwave combination on the left side of this robot cell. And the laser scanner, 2 laser scanner and microwave radar have been configured so that they will allow our mobile robot to pass these safety devices, but nothing else can pass. So humans will stop the industrial robot movement, but the mobile robot can pass all these fences created with safety devices. And in addition to these devices shown here, we also have Kuuppa indoor positioning system that can be used for locating human workers inside our laboratory. This can also be used to locate forklifts and mobile robots, basically anything that is moving inside production facility, or in this case, in our laboratory. Kuuppa indoor positioning system is based on Bluetooth low energy, And we have the beacons in the ceiling, stationary installed, and all the moving parts like workers or forklifts have Coupa tag. It's a small Bluetooth tag with them, and it creates the location for them in order to create digital twin of this laboratory. Our next module is dynamic robot trajectory generation. Idea of this module is to utilize 3D camera for sensing robot work environment. Basically, this module adds vision capability for robot controller. Camera can be any of popular models such as IntelRealSense or Microsoft Kinect. Module provides capability to scan robot environment and to create new trajectories for robot in case of obstacles are detected in current path. Let's say that someone puts an object that is on the robot's path. The module will calculate a new trajectory that will go over this obstacle on the fly. This module is currently based on ROS, but it can also be implemented with RoboDK or AutoMaps. Our third module is online trajectory generation for industrial robot with 3D camera. Also, this module supports many different cameras, such as IntelRealSense, Orbec, or Microsoft Kinect, or maybe even Artec Leo. Idea of this module is also to utilize 3D camera for sensing robot environment, but for different need. This module provides capability to scan workpieces and create new trajectories on the fly or to save scanned data as 3D model file. Camera can be installed on the robot or be stationary installed somewhere in the environment. Our last module is about integrating data needed for robotized production into product design data at very early design phases. This way, it is easy to utilize in production phase and avoidable work in the production phase of the product. Digital context data can also be used when creating a digital twin of the work cell, which can be used in AR/VR experiences for monitoring, operational support, training, safety, and maintenance purposes. Picture on the left shows digital twin of robot controlled with VR equipment. Picture in the middle shows a VR experience for training purposes. Picture on the right presents a VR experience for safety training in mining environment. Here, our first use case demonstration is presented. This use case demonstration is collaborative robotics in large-scale assembly, material handling, and processing. This use case is based on 3 modules shown before. First one is the safe human detection in a collaborative work cell. Second is dynamic robot trajectory generation based on information from 3D camera. And third one is online trajectory generation for industrial robot with 3D camera. This use case demonstration is about enabling high payload industrial robots to collaborate with human workers, and also finding more agile ways of programming robots. Here we present our first use case demonstration video. Idea is to provide drive-in heavy equipment washing service. It is intended for excavators, wheel loaders, and heavy trucks. And let's see how it's done in practice. First, the work object is scanned with 3D camera in order to form a point cloud of this object shown here. After scanning the object and creating a complete point cloud of this object, vanishing trajectories can be created for the robot. This use case can also be utilized in painting, sandblasting, and also in recycled material sorting, such as battery sorting purposes. Our second use case demonstration is integrating digital context to digital twin with AR/VR of the robotized production, and this use case demonstration is based on two modules shown before. First one is safe human detection in collaborative work cell, and second is digital design content based on robot trajectory generation. This use case demonstration introduces new way of working, where data needed for robotized production is included in product data at very early design phases. And first video on the left shows us a use case demonstration for manufacturing building floor elements. Okay, in this video you can see how the information included in building information model can be utilized in robotized production afterwards. This is a building floor element. These points for nailing have been included in the building information model, so it's easy to utilize them when the production phase starts. Also, we can create milling trajectories for heating piping on the floor elements. And for the last layer of floor element, we can use and utilize this information for creating adhesive laying routes or laying adhesive between the floor element layers. And this second video will show how to create AVR experiences from robot cell models. This one is used for training purposes of new employees when the actual floor production starts at the factory. Here we can visualize safety areas. The blue area will slow down the robot movement, and the red area will stop robot movements. And this way, new employees can safely get to know the robot cell before actually moving into robot cell and start working there.
I think, Tero, we need to start wrapping up so we stay in schedule.
Okay, this can also be utilized in aftermarket purposes, where you can see the inner structure of the floor and can take measurements of the floor after the element has been manufactured and it is in use. And actually, this is our last slide. Here we have created digital twins here in Ylivieska from our robot cells, and also our partner university in Narvik, Norway has created digital twins of their robot cells. And now we can remote control their robot cells and they can control our robot cells from Norway. On the left, we can see their window from Robotic, and on the right, we can see the actual robot moving here in Ylivieska. This allows us to share equipment with Narvik, Norway University, and also we have been collaborating with educational purposes, educating their students with our equipment and vice versa. Thank you all for participating. This ends our presentation.
Thank you very much, Tero, for the presentation. But let's move directly to the next presentation by Dmitrii Monakhov from Tampere University, and he will be presenting one of the Tampere University Trinity use cases. Go ahead.
Yes. Okay, let's start. So, hello, my name is Dmitrii Monakhov. I am a project researcher at Tampere University, and today we will talk about our work on the Trinity demonstrator titled Collaborative Assembly with Vision-Based Safety System. So we don't have a lot of time, so let's get started. First, here's a short outline of the presentation. In the beginning, I will very shortly present some motivation for this work. Why is it important? Next, I will talk about the safety model and the general ideas behind it that we use. And then we will look at the structure of the demonstrator and how the different parts of the demonstrator interact with each other. And finally, I will show how this model was implemented for the task of engine assembly. So, first, a little bit of motivation. In recent years, for SMEs to stay competitive, there is a need to move towards sorry, I can see my echo. There is a need to move towards more flexible and intelligent manufacturing, where robots and humans can operate in one space. While such approach can improve the overall efficiency of the setup, it also creates unsafe situations and requires more accurate safety tracking of the environment. So in our work, we define a model to monitor the safety by using depth sensors. We also propose two different types of interfaces for the system, one based on the DLP projector and the other based on the Microsoft HoloLens. The goal of those interfaces is to first generate UI for user to interact with the robot, and second, to visualize the safety border between human and the robot. So let's talk a little bit about how safety model is organized. The workspace that operator and robot use together is divided into two zones. First is the human zone, and human area where operator can perform his lists of tasks, and there is a robot area. These zones are not static. They can change during the assembly process. So for example, robot may need to move some piece into the human zone. So during that movement, the robot zone would be extended to cover both new area of the robot and the part, the piece which robot is moving. So example of that can be seen in the image, in the bottom right image, where the robot is moving the rocker shaft of the engine, and the robot zone is extended by that rocker shaft. So the zones are tracked with the depth sensor. The model tracks the current depth values of the environment and compares them with some initial depth values, which could be stored in the system beforehand or initialized at the startup of the system. If the difference in depth values on the border between zones becomes too large, the robot halts its operation until the user moves away from the robot zone and reruns the robot program manually. Okay, now let's look at the structure of the demonstrator. So the main components include the depth sensor, the robot, the interface, well, let's say generator, and the Linux workstation to run the software. For our case, we used depth Kinect V2 as a depth sensor. We used UR5 robot from Universal Robot family. And for the interface, we used two setups. One with the DLP projector, and the second one using augmented reality with Microsoft HoloLens. So each of those elements is represented as a node in ROS, the robot operating system. And these nodes can send each other data if needed. The depth sensor node collects depth data and deals with nonlinear distortions of the sensors. So the original image is non-uniform across the depth image, and we fix it using the software. Let's say it like this. The data from the depth node is sent to the safety system node and the interface node to check whether operator violates the safety border or if the user has interacted with the user interface. The robot node sends data on the joints of the robot to the interface and the safety nodes to create the robot zone. Yes, sorry, to create the robot, to create the zone around the robot. The robot node can also receive start and stop signals for the robot program. So in this slide, you can see the interfaces we used. So on the left, this is the projector setup, where the border is represented by this blue line around the robot. And on the right is the augmented reality using Microsoft HoloLens, where you can see that the border is this red wall, which you will see in the HoloLens. So the demonstrator was tested on the task of engine assembly. I will now play a short video to demonstrate how this test was processed. So first, the operator needs to install rocker arms while robot picks up the engine frame. Then the robot puts engine frame onto the engine. And then user installs the rocker shaft with the help of the robot. Okay, so we tested the task for both AR and projector-based interfaces. And the experiment was also compared with a baseline approach, where robot and human cannot operate at the same time, and the user have to stay at least 4 meters apart from operating robot. So, okay. So the results have shown that both AR and projector implementations perform better than the baseline in terms of total execution time and robot idle time. So the robot execution time was improved by 21%, and robot idle time was improved by 57%. On the other hand, the difference between execution time between the AR interface and projector-based interface was insignificant. So both approaches are viable in terms of execution time. We also used a questionnaire and some subjective testing to determine which approach users prefer. And surprisingly, AR interface was deemed most unsafe by the users. The reasons which were given from the users and which we saw from the questionnaire were that the HoloLens does not give the full field of view to the user, and the device itself is quite heavy to wear. So operators are not very comfortable to operate with HoloLens. Therefore, projector-based approaches seem to work better for now, until better AR solutions come out. And that's everything I wanted to present to you today.
Thank you very much, Dmitrii. Let's move forward. So we have interesting presentations from the Trinity Demonstration Agile, which is led by Allbesmart in Portugal. And we have Hugo Marques here to present the technical side of this demonstration. And it gives also a good example how the Trinity modules, what have been described here by CENTRIA and Tampere University, how these and other modules by other Trinity partners can also be utilized by the SMEs. Go ahead, Hugo. Go ahead.
So thank you for the opportunity. Nonetheless, it's quite soon for Portugal to start at 7:30 in the morning. But of course, business doesn't have a specific time schedule. Okay, so the presentation I'm making is on behalf of the team of the Agile project, which is one of the experiments being supported by Trinity. The Agile consortium is composed by two SMEs. Allbesmart is an SME from 2015, so it's roughly 6 years old. It's on the end of the startup life cycle. It's very stable at the moment, very good number of customers, and Stone Shield as well, a little bit more sooner than Allbesmart, but also already a very interesting industrial manufacturer for robotic machines. Both of these companies are Portuguese, and this is the background that brings us to here. We are focused basically in Portugal. We have a very strong affinity with the electric cable automotive industry, and specifically in the city where we are, we have a few key companies, worldwide leaders on their sector, and we are focusing on basically on the manufacturing of electrical cables, which currently require much manual work. But nonetheless, just for you understand the context, before COVID, we had around 90+ million vehicles manufactured every year. And if you count all the electrical cables that are manufactured around the world, 60% of these cables are going directly into these automakers in these vehicles. But the question is that most of the electric cable assembly is done manually, and we use cost labor countries for that. But due to the requirements of miniaturization, these electrical cable manufacturers are more and more requiring robotics and the assistance of machines. And this means that the workers need to be trained, and the way they interact with the machines also needs to be rethink. And this is where Trinity provides us with the inspiration. In the value chain, if you look at the figure, you can see that Trinity provides us this mentorship, the use cases, the documentation, all this knowledge that we can access on different areas: collaborative robotics, augmented reality, artificial intelligence with machine learning, and the funding. Then you can see that Allbesmart is the technology provider, and it provides this technology two companies. Specifically in this case that I'm presenting here, our customer or our partner on this project is Stone Shield. And Stone Shield is the integrator of the robotic machines. I will go back one slide just to show you, in this case, a small video just for the machine that we are talking about. This is a robotic seal inserter. As you can see, it is not a collaborative robot in this case. So the robot is enclosed to protect the technician. And what you have is you have small components which are cable connectors. And in this picture, you can see that the connector will have some seals. The seals are some plastic protection units that you put in order for the cables for the connector to be sealed, either through air or humidity, etc. And in this case, the robot has different types of grippers. It depends on the connector, and based on this, it will perform its action. Okay, so this machine, of course, is semi-automated, and we are working on top of this machine to provide augmented reality and also to provide classification for these connectors that you are seeing here. So I will go back to my presentation. And Stone Shield then has a list of customers. They provide these machines per request, so they are customized machines for specific cable manufacturers. In case you are not familiar with the industry, Yazaki, Leoni, and Aptiv are the most well-known cable manufacturers for vehicles. And then, of course, they have their own clients, and this could be BMW, Audi, Ford, well, Ferrari, etc. So Agile focus on three use cases, as I was saying. It was inspired by three use cases from Trinity. The first use case, which is the collaborative assembly with vision-based safety system. In our case, we are using this to make a collaborative assembly of electrical fuse boxes. I will explain you later, well, immediately after. Then the second use case, which I will not focus on my presentation today because we will not have the time for that. It's based on augmented reality. So we are providing an augmented reality interface. And the second use case is based on a bin picking process in which we have to sort connectors that have been used in different boxes. So the boxes, the connectors that come from this machine, then we, at the output, we sort these connectors and put them in different boxes through classification. So let's start with the first use case. Our goal here is to use a slower robot. It's a collaborative robot that allows the technician to mount specific fuses on the fuse box that you can see below, and then the robot will assemble the other fuses. So this can be made while the technician is not on the station or while the technician is on the station. So that's why it is a collaborative use case that we are exploring. We have a specific assembly station. Here on the figure, you can see that we are planning a station with 3 fuse boxes. For the time being, we are just working with 1. And you have all this red line here, and this red line is our projected safety line, as was being explained by the previous presenter, when we are using safety, because this is a collaborative robot, and we provide the technician with a visual guidance where it is safe for him to operate. Nonetheless, the robot also has its safety zone, and it's a collaborative robot, so the velocities that are in place here are slower than normal. But anyway, we have a goal, and our goal is to reach 30% decrease in the cycle time for a fuse box assembly. So by putting the assembly in a collaborative process with the robot, we estimate that we can reduce the average time for 30%. I will just show you this small video. Again, this is not the final product. This is just something that we are still working on. So the initial position of the fuse box, it's pre-coded, and then we have a delta for the next fuses and then we will insert the fuses in the fuse box. Of course, the feeder for this demo that you are seeing is not the final feeder that we want to use. Here we are showing you different types of different sizes of fuses, and you can see that the robot arm, the gripper, it's a little bit bigger than what we originally were requesting for. So this is something that we have been doing now. It's we have machinate, we have designed, and we have requested the manufacturing of a new gripper, which will be shorter, and this will allow us to pick up smaller fuses, which currently we cannot do. Also, the feeder system for the fuses here is just for our training, but you will see that, well, in the next iteration, we will have a different type of feeder for the fuse. Then in our third demonstrator, we have bin picking process. At the end of the machine, you will see here on the bottom of the screen, the machine that I was showing you before is producing many connectors. For quality, these connectors needs, well, we use many connectors to train the machine and to make sure the machine reaches a very high percentage of efficiency. So when the connectors are assembled, being they okay or not okay, at the end we need to reassemble the connectors. So we receive the connectors in boxes, and then we have to sort them. This was originally a manual process, and what we want to implement with this project is to actually identify the connectors automatically, and based on their classification, to put them on different boxes. You can see here that we have to make different types of calibration, because we use different systems of coordinates. First of all, we have the system coordinate for the robot arm, which is represented here by the B. Then we have the system coordinates for the robot arm camera, which is the G. The G here is from the grip of the robot. Then we have a 3D camera vision system, which is based on Intel RealSense, which has a different system of coordinates. And then we have the connector that we want to identify, which also has a different system of coordinates. And the challenge is for us to actually make all these three systems of coordinates to work together in order for us to not only identify and recognize the object, but also to pick it and then to place it in a different box. Here I will show you the first part of the assembly process, well, the recognition process, which was also inspired by Trinity, because we are using YOLO. We are using the latest version of YOLO, which is an algorithm that was created by Facebook, and basically it's very granular. It allows us to perform specific modifications on the algorithm for a specific use case. So let me show you that here what you're seeing is the 3D vision camera, and this is the automatic object classification based on the results from the training. So you put different objects. First you facilitate, you put lower objects all on the same place, and then you sort the objects and you train the machine learning algorithms in order for it to recognize that the same connector can be on different places and on different positions. And we have achieved for the time being a very interesting rate of success in terms of object classification. So you will see that I will just speed up the video and I will show you that at the end you have different backgrounds on the objects and still it is able to detect the objects. So this is something that was taken us some time, because as I was saying, it is a challenge to make the system of coordinates to be synchronized between all the variables that we have in our system. And here I will just show you a small video. Well, not so small, but well, 1.5 minutes. So here you have different connectors. The robot detects the connector and then places it in a specific orientation. So the orientation is something that we are working currently. We need to make sure that the objects are oriented. It could not be, it could in this case not be oriented, but we are challenging ourselves in order to make sure that we ensure not only the correct sorts, but also the correct orientation of the object. I'm speeding up the video here because, as I said, this is a collaborative robot, and as such, it is slower. And for the last piece, we would like to show you that the orientation actually is being quite a challenge for us, because here you will see that the robot will have to decide the best way to pick this object. So it makes different visualizations for the scene, and then it decides that the centroid for this object, it's in that position and it's exactly where it should pick the object. And you can also see the objects are oriented at the end, because at the end we have these two, maybe you cannot see it, but we have the red line and then we have this purple bluish line. And when they match, this means that we have achieved the right orientation. And this is something that it's not yet 100%, but we are still working on it. So that's it. At final remarks, we would like to just clarify that why should the companies actually use mechanisms such as the ones provided by TRINITY. First of all, TRINITY has thought on a very large number of real use cases. It was really because of this large set of use cases that we have identified the ones that were more applicable to us. And these are very well documented and provide you also a very good understanding how you can actually adopt those use cases in your scenario. Also provides valuable feedback in different technological areas. We are just here focusing on 3 of them, which is the collaborative assembly with vision-based safety system, the human-robot interaction for the augmented reality, which I didn't show in this presentation, and artificial intelligence with machine learning for object detection and recognition. Of course, TRINITY also provides us with events, dedicated events for visibility and matchmaking. And we have yet to start our collaborative publications, because as you can understand, publications will not result at the beginning of the project. It will start appearing at the middle and afterwards of the project. And this is something that we are now trying to focus. So that's it from my side. Jyrki, if there are any questions and I can answer, I will be happy to.
Thank you very much, Hugo. I think this is a great example on how the TRINITY modules can really be implemented and utilized. And I find the machine learning part very interesting, because that's a very hot topic at the moment. And as you mentioned, the finding the components is not that big of an issue anymore, really, but then how to find them or how to decide how to grip them and what's the best option for the robot, that requires quite a lot of work, which quite often tends to be forgotten in the when you talk about machine learning in this kind of computer vision applications. But thank you very much. Any questions for Hugo? The presentation will be uploaded to the TRINITY YouTube channel, so you can of course watch it again, and you can contact Hugo or Paulo or others at Allbesmart for more questions. The slides will also be available, so you can get the contact information from there for that one. Thank you very much.